Assalamualaikum and good day. I'm Hasib bin Muhammad and today I'm going to present our last lab activity, that is lab 4, 3-phase synchronous generator. The objective of this task is to demonstrate and explain the operating characteristic of 3-phase synchronous generator using synchronous motor generator and prime mover or dynamometer modules. For this task, we are required to use a LV simulator from LabBot. In the screen is the web interface for the simulator. On the screen is the wiring diagram that we need to view. Okay, first let's identify the module that we need. Power supply, prime mover, synchronous motor or generator. Before connecting our circuit according to the wiring diagram, let's take a look at the function of our modules. Power supply. Our power supply, we have a capability of supplying 24 volt DC and 124 volt DC. Our prime mover will need 120 to 150 volt DC and low power input of 24 volt DC. Our synchronous motor or generator will act as a synchronous generator. The exciter will be supplied with 124 volt DC and the coil will connected and measured by our data acquisition system. Our positive DC on port 7 will be connected to the prime mover. Let's change the color to differentiate between the neutral power line and the live power line. DC supply from the port 8 will be supplied to the synchronous generator exciter. Again, let's change the color to more visible one. Low power input will be connected to our low power input, and our DAI also required a 24 volt low voltage supply. The output from our coil will be connected to our DAI. There are several measurement interfaces. We can measure the voltage, we can measure the current, torque and the speed. Torque output will be connected to the torque terminal. Speed output will be connected to the speed terminal. The output from the coil will be connected according to our wiring diagram. For this experiment, prime mover will pull the synchronous generator and the generator will generate electricity from the movement from the speed of the rotor. Therefore, we need to mechanically connect the two motors by using the belting function. From the experiment, it is required to turn the exciter switch to close and the exciter knob to 3/4. Prime mover mode will be set to prime mover. Okay, change the voltmeter selector to port 7 so that we can control our prime mover speed. First, turn on the power switch and then turn on the switch, and here we can increase the voltage of our prime mover. The result can be viewed by using our oscilloscope. Set channel 1 E1, channel 2 to E2, channel 3 to E3. Select the continuous refresh mode, channel 4 to I1, and there we should have all our voltage. We can also view the result using our metering function. Set the view, click layout, select layout 2, the number of column 3/2. Here we will have our E1, 2, E3 and I1. Select the continuous refresh and we shall see our reading.
Assalamualaikum and good day. My name is Muhammad Ikram Hakimi bin Saifuniza. For this lab, I will present the result for synchronous generator no-load operation. Okay, for this lab, the waveform form the sinusoidal shape, then the approximate phase shift between each of the voltage waveform is 120 degree. Then for the result, the in the windows in the oscilloscope windows, when the voltage when the speed prime mover approximate equal to 1000 for the speed, the waveform is like this, like the shown. Then how do the amplitude and frequency of the voltage waveform vary when the speed of the synchronous generator is decreased? The explanation is like this. As the speed decreases, the amplitude and frequency of output waveform decrease. Frequency is the time required to the armature to complete a cycle. Hence, frequency equal to speed over 16. Therefore, the speed decrease, generated frequency also decrease. Generator voltage also decrease as the speed goes down as V is proportional to armature speed. For the other question, does varying the speed of the synchronous generator affect the phase shift between the voltage waveform? Why? The answer is no, because phase shift remained the same because the phase shift is dependent to stator arrangement. For this experiment, synchronous generator with 120 degree stator displacement was used. For the next question, how does the amplitude of the voltage waveform vary when the field current of the synchronous generator was decreased? Okay, so the waveform shown like this, then as the excitation current decrease, generated voltage slightly decrease. The field current reduced magnetic field around the coil will weaken and reduce magnetic flux intensity around the stator, hence reducing generated voltage. For this question, the answer is just like same as for the first question, because the the phase shift is not dependent to excitation current because dependent but is dependent to stator displacement and armament speed.
Assalamualaikum and good day to all. I'm Muhammad Izham bin Ahmad. Next, I will present in this experiment for part 2 and I will explain how to do the connectivity. In this part, it's similar with part 1 but just a few modification or addition in this circuit. So this is the diagram and we need to make a connection by following this figure. First, we need to place the right module to do the experiment, which is a power supply, prime mover, synchronous motor, data acquisition interface or DAI, and also the additional module is resistive load. Okay, now we need to connect all the module by following the diagram in the lab sheet. Okay, first we connect the power supply to synchronous motor and resistive load. Okay, next we are going to do the connection between power supply and prime mover. And terminal to N terminal and 7 terminal to input. Okay.
And also we need to supply the current to prime mover module and DAI module. So connect to low power input terminal. And then as shown as at the figure, we connect synchronous motor to the DAI to get all the data. And the last part is top output from prime mover to data acquisition interface DAI. Speed. Okay. So the connection is complete, and then make sure all the selector at the module in the right position. Okay, first check for prime mover. The display must be in speed position and mode in prime mover position. Okay, so for the synchronous motor, make sure the exciter knob must be in 3/4 position, and exciter switch must be in 0 position. Okay, so for the resistive load, make sure all the switch in 0 position. Okay, so up to here my explanation for connectivity, and my friend will continue to capture and explain the result we made. Okay, all right, thank you.
Assalamualaikum and a very good day to all. My name is Hadira and I will continue with the part of explaining the results that my lab mate Muhammad Izham has produced before. I will continue from step 12 until the end. But first and foremost, I would like to thank my lab mates Muhammad Izham and Hasif, because without them, I cannot have done this alone. For step 12, I will have to record the synchronous generator's output voltage, field current, frequency, and speed, and tabulate them in a data. Then I will have to change the value of the resistor R1 and vary the settings of the exciter knob to increase the field current of the value indicated in the table 6.1, which is this one. And again, after the setting of the exciter knob, I will have to record the data again in the data table. For step 13, we short circuit the resistor R1 using a connector LED, and then on the synchronous generator, we turn the exciter knob fully clockwise to set the field current IF to maximum, and then we readjust the prime mover so that it is equal to the nominal speed of the synchronous motor, and we record that in a table. And then we set the prime mover to 0, and then only we turn it off. For step 14, we confirm the data that has been stored, and we print the data table in the data table window. For the next step, we are required to record the frequency of the voltage produced by the synchronous generator. And then I will have to calculate the theoretical frequency of the voltage produced by the synchronous generator, and here's the way. In the next step, we are required to obtain a graph with an appropriate settings in the graph window, and this is about obtaining a graph of the synchronous generator output voltage EO and the field current IF. So the x-axis will be the synchronous generator's field current, and the y-axis will be the synchronous generator's output voltage. And here is the graph. In step 17, we are required to turn the power supply on, and on the synchronous generator, we have to set the exciter knob so that the field current indicated by meter 1, which is the IF, is equal to the value of IF given in the table 6.2, which is 500, 300, 300, 300. So here is the result of step 17. We could see here, this is at nominal speed, which is the 1800 RPM. We could see the generator's output voltage is 126.8 volts, and then the speed is 1804 RPM, and the field current is 0.753 amperes, and the frequency is 60.14 Hertz. So here is the result of step 17. We could see here, this is at nominal speed, which is the 1800 RPM. We could see the generator's output voltage is 126.8 volts, and then the speed is 1804 RPM, and the field current is 0.753 amperes, and the frequency is 60.14 Hertz. And here is the last result for step 17, which we are required to do for field current when it is 300 milliampere. Then in step 18, we are required to record the synchronous generator's output voltage, field current, frequency, and again the speed n in the data table. And we have to increase the prime mover speed to the value given as followed in the table with the increment of 200 RPM. So for the results of step 18, here is the speed when it is at the nominal speed, or 1800 RPM. The generator's output voltage is 126.1 volts, while the speed is 1804 RPM, and the field current is 0.741 ampere, while the frequency maintained at 60.14 Hertz. Now, because the steps makes us increase the prime mover speed with the increment of 200 RPM, here is the speed at 2000 RPM. While here is the speed of 2200 RPM. And last but not least, the speed when it is 2400 RPM. I think that's all for my part today. Thank you for listening. And again, I would like to thank my lab mates for being really patient with me in getting my part of the video. And especially to Hasif and Mama Izham, because they have been really, really kind with me and with their guidance. If it isn't for their guidance, I would probably cannot make this video.